Okay, Jaume, let's see. Are you ready?
Yes.
We have 90 minutes, just inform you. Okay, let me introduce. Let me just see what everyone. Okay, great, that's fine. We can start. Welcome, everyone. Bienvenidos todos. Welcome to Harvard CMSA seminar series on quantum matter in math and physics. Today, we are very honored to have a Professor Jaume Gomis from Perimeter Institute for Theoretical Physics. And he will be telling us some story he recently done on this global anomalies on the Hilbert space. Let's directly welcome Jaume. It's all yours.
Okay, well, thank you very much, Jaume. Thank you very much for the invitation to speak. And actually more broadly, thank you very much for organizing this series. I've been really learning lots of things from all the talks. Whenever I can, I join live, and or if not, I follow it, I view it later. Yeah, so I'm going to describe some aspects of work that I did with his colleagues at Perimeter. And so Diego del Mastro, which is my student, and Davide. And I was hoping that I'll be able to say some more about the work in progress with Diego and Matthew Yu, which is also my student, but I think time constraints will not really allow it. But, so the topic of the seminar is about a subject for which I think there has been like tremendous amount of progress in the last few years. And I think it's very suiting for this series because it's really extremely interdisciplinary. It has had kind of deep insights from both condensed matter, particle physics, and mathematics. So it's an extremely, I think it has been an extremely vibrant area of research in the last few years. And there have been really new results that have led to new answering long-standing questions in the field, both in particle physics and in condensed matter. So in this talk, what I want to present is, well, so there will be some part that we will just set up what the problem is. But essentially, the main thing I want to do is to provide a very simple mechanism to detect whether a system has a global anomaly that does not rely on the usual tools that one needs to detect whether a system has a global anomaly, like eta invariance and such things. So that will be the main goal. And actually, and then will be some story about how the classification of anomalies has a certain mathematical description. And we will see how this mathematical description that enters in the classification of anomalies has a nice physical interplay with the way the anomalies are imprinted in the Hilbert space of the theory. We will see that different structures have different representations in the Hilbert space. And then finally, a very fun application of all of this will be the fact that due to the fact that some systems that have certain types of anomalies, they will imply that they have, and that includes for strongly coupled field theories, including probably the most interesting cases in 3 dimensions. We will find that by virtue of these theories having anomalies, certain types of anomalies, it predicts that the spectrum of this theory is supersymmetric, even though the quantum field theory that we're studying is strongly coupled and not supersymmetric. Very good. So let me start. By the way, so usually it's already awkward enough to hear oneself speak giving a seminar. And now it's even worse because I have to hear and see myself. So please stop and ask me questions or make comments so that it doesn't feel like I'm just talking to myself. And yeah, so I invite comments and questions very much. Okay, so let's start with some kind of background so that everyone is on the same page. So I mean, of course, symmetry is an extremely powerful organizing principle in physics. And as we study more and more, we realize that there are more and more types of symmetries or things that extend the notion of symmetries. So of course, from the very old days, we're familiar with the dichotomy between discrete and continuous symmetries. And roughly speaking, you can also classify symmetries as being space-time symmetries, like the Lorentz group, time reversal, parity. Or in discrete symmetries, you could have crystallographic, supersymmetry, magnetic symmetries, and also kind of internal symmetries. But of course, these two can be tied together because you can have a flavor symmetry that contains, say, -1 to the f, a fermion number. In more recent times, it has become clear that there are other types of symmetries that are not in textbooks, but they should be, and they also play a very important role in quantum field theory. And these are go under the name of higher form symmetries that, instead of acting on the local operators of your theory that we're used to, they act on higher dimensional operators. And sometimes these notions of conventional symmetries and higher symmetries combine into higher structures that are called 2 groups, 3 groups, and so on. Okay. And even more recently, if one is generous enough by what one means by symmetry, there are other types of objects that one could use, and that sometimes are known as non-invertible symmetries that could be used also to constrain the dynamics of your theory. Okay. So what are symmetries good for? I mean, they're extremely powerful because essentially what they allow to do is to parameterize the possible dynamics of a physical system. So what they do is they constrain unrelated observables and imply selection rules. So essentially, by using symmetry, you can parameterize the most general answer that your system can have, but which is wonderful, and it's huge progress already. But symmetry alone does not say absolutely anything about the dynamic of the system, unless you have kind of an integrable system in which essentially symmetries alone overdetermine the dynamics and fix the dynamics completely. But more broadly, symmetry does not really tell you anything about the actual dynamics. So, of course, I mean,
can I ask a question since you invited us to interact with you?
Yes, please.
So this definition of symmetry here, if you go back to it.
Yes.
So as a mathematician, that is something I always want to try and distinguish what the symmetry acts upon. So do you mean by that symmetry of an equation, symmetry of solutions? Because the phrase symmetry of possible dynamics is ambiguous for me. What is the asymmetry of?
I allow for the most, so essentially I would say is any set of actions that give rise to relations between correlation functions via word identities. So by that I allow myself the usual notion of symmetry that you would find in a textbook, but I also allow myself perhaps this notion of, which is a bit kooky in usual sense to call it symmetry, but that they also lead to kind of word identities for correlation functions.
Okay, so it's in the context of variational problems, essentially.
Yes, yes.
Okay, thanks.
Yeah. Actually, this is a good point, though. I wonder whether this way of definition from the symmetry of correlators relate to what the usually condensed matter solve, just finding some operators commuting with Hamiltonian. That it basically is more like a UV point of view. I still think I don't know what the answer, but I think the way, for example, like Xiaogang is here, the way we look at the global symmetry on a UV regularized complete system is finding some operators. It could be just the whole space-time dimension, or maybe some co-dimension, low-dimensional operator commuting with Hamiltonian. And that's a way we say global symmetries. But yeah. Here seems you are using a definition from the correlators. While some maybe more people who are more familiar with Lagrangian or path integral formalism may use the way to look at the symmetry transformation makes the partition function or path integral invariant.
So the reason I'm using this point of view is several. So first of all, as you know, there are certain quantum field theories for which we do not really have a Lagrangian description. So being married to the Lagrangian is problematic. Also, this other point of view means that there are systems that have symmetries that are not, sometimes we use the nomenclature quantum symmetries. So these are symmetries of the correlation functions, essentially symmetries of the theory, but they're not symmetries of the Lagrangian. But they're symmetries of all the observables. I also don't want to commit to things committing with the Hamiltonian because the Lorentz boosts do not commit with Hamiltonian, and they still constrain the dynamics.
Mm-hmm. Yeah. Thanks.
So now that we have used the symmetry as powerful as we can to kind of write down the most general answer that the system could have, we still have to solve for the dynamics. And of course, that's notoriously difficult to do. So when your system has small quantum fluctuations, you can solve for the dynamics just using perturbation theory, some Feynman diagrams. But the point is that for strongly coupled systems, there is no really systematic or universal tools to solve the problem. And that's we are stuck with really solving systems where strong fluctuations are dominant. Okay. So an important exception to this statement is that exactly the subject of tooth anomalies, which do tell us something about the dynamics of the actual system. Okay, so of course I'll describe in more detail, more systematically, what the tooth anomaly is, but let me just say now that it does two things. Well, the main thing it does is that it does tell us something about the dynamics. But so what is the tooth anomaly? The tooth anomaly essentially is a violation of a symmetry when we couple the system that you're interested in, to background gauge fields for those symmetries. Okay. And you see some kind of violation of the word identities, if you wish, of your system. Okay. Why is this very powerful? And as I will describe later, I'll go into more details about this later, of course, is that the reason this is powerful because anomalies admit a topological classification. So they are kind of quantized in some way. And since they're quantized, they're invariant and they're continuous symmetric deformations, which include the scale transformations. Okay. So in particular, this is very useful both in condensed matter and in particle physics, because sometimes you know you're Hamiltonian at very short distances, but the dynamics become strongly coupled at long distances, and you don't really know, you don't really have a clue how to answer what happened at large distances. But one thing that you do know is that if the system had any tooth anomaly in the ultraviolet, it will have to be saturated in the infrared for whatever dynamics you propose, because the anomaly is scale independent. Okay. So when a system has a tooth anomaly, it allows us to immediately make some very powerful conclusions that go well beyond what symmetries will allow us to conclude. Okay. So sorry, someone raised their hand.
Yeah, can I ask a question?
Of course.
It's a follow-up question of Jaume's. Suppose I'm giving a set of correlation functions and I notice some relations between them. For example, some of them are equal to each other.
Yes.
Then is it guaranteed that this relation is due to symmetry? Or if it's not, then how do I know when it's due to symmetry, when it's due to some other reason?
I mean, if it's due to symmetry, you'll be able to say how the symmetry acts on your operators in the theory. Yeah,
but suppose I have a theory and suppose I know all the correlation functions.
Yeah.
And how do I know? If I notice some relations between some correlation functions, how do I know there's some operators that transform one correlation function to the other?
Well, so I think in general, if you only know a subset of the correlation functions, it will be a priori not possible to know that whether it's a symmetry or not. That's why, for example, it's hard to know whether a system has a quantum symmetry or not, because in a sense, you need a priori a set of relations that involve all operators in the theory. In principle, operators could be charged, and you need to know the relations between all of them. But maybe I mean, this is more of I'm happy to discuss this later, but I think this will take us too far afield to try to define more. I mean, go more deep in this direction. We will soon work with very concrete examples of symmetries that you know and love, not abstractly what could be a symmetry or what could not be a symmetry.
Okay, thanks.
Yeah, so one thing that we know about tooth symmetries is that it allows you to, if the system has a tooth anomaly, it allows you to say something non-trivial already about the low energy structure of your theory. In particular, it tells you that if a system has an anomaly, the ground state cannot be trivial. And the reason is that the trivial theory does not have any anomalies. So that's already something that you can say immediately. And therefore, it leads to constraints that the candidate dynamics that you're trying to solve for will have to satisfy, will have to match whatever anomalies you have. Okay. So before, this was a bit too abstract, let me give you two examples of how tooth anomalies can tell you something powerful about the low energy dynamics of your theory. So consider, for example, this is probably a well-known example, but let's consider a spin a half chain on a circle. And this guy is just the usual SU2 Heisenberg spin chain. So you have a spin a half in each side. And this guy has an SU2 symmetry. So of course, all states will be in representations of SU2. Okay. But now imagine we do something and we allow we deform the Hamiltonian by writing down the most general Hamiltonian that couples an even number of spins. It could be nearest neighbors, it could be non-nearest neighbors. And we allow couplings that in general will break the SU2, SO3 symmetry of the spin. Okay. Now, what can we say about this system? So now you can try to just say plug it into Mathematica and try to find the eigenvalues of and eigenvectors of this Hamiltonian. And you would naively say that there is not much you can say about it because it's a mess. But the reason that you can say something useful is that actually this symmetry has a time reversal symmetry, t squared equals 1 symmetry. Essentially because, because as you know, time reversal acts on spin by reversing it, okay? So if you write down terms in the Hamiltonian that are even a number of spins, the Hamiltonian will be time reversal invariant, okay? Now, and the thing that you realize is that for when the number of sides is odd, when the number of sides is odd, actually this symmetry, the Z2 symmetry, is realized projectively on the Hilbert space. And the reason is that essentially the operator that implements this transformation is essentially the sigma 2 Pauli matrix. So let's say for one side. So t squared is essentially, remember that t is antilinear. So it's sigma 2 star, which is -1. Okay. So while time reversal is realized vectorially in the usual manner with t squared equals 1 on all operators in the theory, it is realized projectively on the Hilbert space. And that's the usual signature of having an anomaly in 0 + 1 dimensions. So you have an anomaly for this symmetry. And since projective representations cannot be one-dimensional, this immediately tells you that the ground state is doubly degenerate for an arbitrary type of Hamiltonian of this type. So by using the fact that this system has a 't Hooft anomaly for time reversal, you learn something non-trivial. Essentially, it tells you that the spectrum of the Hamiltonian, including the ground state, is doubly degenerate. And that's just a consequence of the 't Hooft anomaly. So there's something you could have concluded even without going to Mathematica if you realize that the system had a 't Hooft anomaly. And this essentially is, in some guise, Kramer's theorem in action. Okay, so now let me discuss another example that's more recent, where 't Hooft anomalies led to some important. It was an important clue into proposing the dynamics of a certain strongly coupled gates theory. So let's consider an analog of QCD, but in 2 + 1 dimensions. So let's consider SUN Yang-Mills coupled to a Majorana quark in the adjoint representation. Okay. So we understand this theory well in the ultraviolet, but we want to know what happens in the infrared. Is the theory trivial or non-trivial in the infrared? Okay. So something that you can say about this theory is that that's quite easy to figure out, is that this theory has a Z4T time reversal symmetry, where now time reversal, as opposed to the one before, which was a bosonic symmetry, is squares to -1 to the f, where -1 to the f is a fermion number that acts as +1 on bosons and -1 on fermions. It turns out it also has a Zn one-form symmetry, okay, that essentially acts on the Wilson lines of this theory. Now, the fact, now you can also, which that's a bit harder, but you can figure out that this theory in the ultraviolet has a certain 't Hooft anomalies for these symmetries, okay? So this immediately tells you that the theory cannot be trivial in the infrared. So something in the infrared must be happening that is able to saturate the anomalies for time reversal and one-form symmetry. And essentially by kind of using these ideas and other ideas, one can write down an answer for what the infrared dynamics of this theory is. So the details don't matter here too much. It's just some particular Chern-Simons theory on a decoupled fermion. And of course, one of the important tests that the proposal has to satisfy, and it does satisfy, is that the anomalies of this low energy system, Chern-Simons with the fermion, are match those that you can compute in the deep ultraviolet, where you just have a system of fermions in the deep ultraviolet. And so essentially by using the constraints of 't Hooft anomalies, you can arrive at an answer and lead to surprising physics in 2 + 1 dimensions like deconfinement, emerging anions, and gauge fields, and so on. So this is just to give you a flavor of what strong consequences 't Hooft anomalies can have for the dynamics of a quantum system. All right, so now I'll give a slightly more systematic treatment of Tooth anomalies and their classification. And then we will proceed to learning how to detect at least some of the anomalies by very simple means, essentially using methods that you could learn in the first course in quantum field theory. Okay, so as I said, what is the unofficial definition of a Tooth anomaly is when you have a system that has a global symmetry, you couple it to background Gates fields for that symmetry, and we're going to call this background Gates field A, okay? And essentially you have a Tooth anomaly with a non-invariant to the partition function and a background Gates transformation, so in general will transform by a phase, cannot be cancelled by a local counterterm. If it can be cancelled by a local counterterm, we don't call an anomaly. That's just something that you can be removed by a change of regularization scheme. Okay. So this kind of definition, which I guess is the one that Wes and Zumino really coined, is what gives anomalies very much of a cohomological formulation, because it's like a D equals 0 modulo exact things. Okay. Now, what can we say about this violation, the anomaly here, alpha of G of A? So alpha is the anomaly, and it depends on the transformation and the background connection. Okay. So this guy obeys a certain, so this is a long story, so I'm just cutting corners here, but to just give you a basic flavor of what the kind of constraints that the anomaly has to satisfy. First of all, it has to be a local function of the connection and the Gates transformation. And it has to obey a certain set of relations that you could think of as associativity. Essentially that the transformations concatenate properly. So in the for continuous symmetries, these are the famous Wes-Zumino consistency conditions, okay, that give rise to the usual cohomological formulation of anomalies. Now, this statement I made here is both true for continuous and discrete symmetries. And of course, a lot of the excitement in the last few years has been in a deeper understanding of anomalies for discrete symmetries. Okay. So now, what is the analog of the Wes-Zumino consistency condition of continuous symmetries for discrete symmetries? So one point of view about this is the following. So one way to formulate coupling a system to a background connection A is that you can equivalently represent coupling the system to background connection A for symmetry G as putting in your system a network of topological defects that implement that symmetry. Okay, so then the Wes-Zumino consistency condition is replaced by a pentagon-like identities for these discrete symmetries that essentially tell you that under a Gates transformation, your network of topological defects that implement that realize the bundle describing the background G connection changes, and it can change up to a phase, but then you have associativity relations that give rise to the pentagon-like identities. Okay. So there was a question somewhere. Sorry, I cannot read the question. So if you can just.
I think this person, I'm not sure, Behar, is just trying to say whether this big A, capital A, is the Young-Mills field.
No, so
as you know, it's non-dynamical background gauge field, which
so it's a fixed background connection. Is something that we do not path integrate over. So if you wish, it's the source for the symmetry, but it's not dynamical. That's a very important point. It's not dynamical. Okay, you can gauge it later if you want to, but well, you won't be able to do it if you have a Tooth anomaly. But for now, it's just a background gauge field for a global symmetry. That's a good question. Yeah. So something that was realized early on, and it has been developed in recent years a lot. This was not well understood for the case of continuous symmetries, but now it has been much better understood in the context of discrete symmetries, is that the anomaly, essentially this phase, is captured by inflow from a topological term in one higher dimension. Okay, so essentially the anomaly can be thought of as arising from some topological term in one higher dimension. Okay, and physically, this topological term describes what it's called SPT phase in the higher dimensional space. An SPT phase protected by the symmetry G. Okay. Now, what is the relation between the SPT phase and the anomaly? Well, the point is that if you now consider the SPT phase not on a closed manifold but on a manifold with a boundary, the anomaly is reproduced by considering the transformations of the topological term in the presence of the boundary. So there is a deep interplay between anomalies in D dimensions and SPT phases in D+1 dimensions. And that's where a lot of progress has happened in the last few years. Okay, so since anomalies are classified, they have a cohomological flavor, they're described by quantized topological classes. Okay, and the thing that is not in text, but again, it will be, is that historically anomalies only happen in systems with fermions, like, you know, triangle anomalies and stuff like that you learn in field theory. But another point is that actually anomalies can happen not only in fermionic systems, but also in bosonic systems, and both for discrete and continuous symmetries. Since the anomalies are quantized because they're topological classes, essentially, they're robust under G-symmetric deformations. And in particular, they're insensitive to adding new degrees of freedom. And in that way, if you wish, anomalies is a big invariant in the space of quantum field theories, because it doesn't change as long as you don't mess up the symmetry. So it kind of allows you to probe the homotopy in the space of field theories. Okay? As I already argued that since it's quantized, it cannot depend on the scale and gives rise to these anomaly matching constraints where the 't Hooft anomalies in the ultraviolet have to be saturated by the ones in the infrared. Okay, and just to hammer the point that why these things are interesting is that the 't Hooft anomalies allows us to give us some information. It doesn't tell you what the answer is, but it tells you what the answer is not, about what can happen in the infrared of some strongly coupled system. Okay? So that's why they're extremely powerful, and one of the very few tools we have really to say something about strong coupling dynamics. Okay, so now I have to say a few things about how anomalies are classified from, and then try to give a kind of physical interpretation of this. What's going on here? Okay, so I'm going to use the following language, and I'll just explain what the physics is. So let's study with bosonic symmetries, bosonic systems. So systems that do not require a spin structure when you study them. You can, okay. So that the symmetry data of a bosonic system is described by the following pair. So you have a G, which is a group, and then this W1 is some element. So it's a map between G, the group G, and Z2, and that's essentially physically what the statement that we know from textbooks that in quantum mechanics, symmetries can be either unitary or anti-unitary. So essentially, this W1, this map from G to Z2, tells you whether the transformation is a unitary transformation or anti-unitary transformation. That's essentially Wigner's theorem, that the symmetry is either unitary or anti-unitary. So in order not to sound abstract, consider the group G be Z2. And then the types of transformations you can have, this unitary to anti-unitary, is labeled by this H1, which is a Z2. So now, if W1 is 0, you just get the standard unitary Z2 symmetry, while if W1 is 1, then you have the Z2 time reversal symmetry. Okay, so you see that W1 essentially tells you the information about whether the symmetry is unitary or anti-unitary. Okay. The outcome of a lot of work by many people is that bosonic anomalies are classified by a certain twisted cobordism group that has this name. So the input data is the group G and this structure that tells you whether the symmetry is unitary or anti-unitary. Okay, and this was developed by starting from models that, and then the sharper formulation came later. Okay, so I'm not going to try to define very carefully what this cobordism group is. I will tell you the details that will matter for us later. So one observation to make is that this twisted cobordism group reproduces group cohomology when the dimension is not too large. Okay, and this extends really the classic result that anomalies in quantum mechanics are classified by projective representations, aka the second cohomology group with values in U1. Okay. So this.
Sorry, the coefficients are twisted, right? Here, the U1 is twisted.
Yes, absolutely. Yes. Yeah, so I'm not writing that extra data not to make things more clear, but indeed, if you have an antilinear transformation, the coefficient should be twisted by that. Yeah, exactly. Good. So we see that this structure generalizes things that we knew from in lower dimensions and gave rise to kind of a more refined set of anomalies than we thought were possible, that were before labeled in terms of group cohomology. So, and the more general group that computes the classification of anomalies can be obtained from a spectral sequence that contains this group cohomology, which is the naive answer you would have obtained, but is corrected by cohomology groups of lower degree. So instead of D plus 1, you get D minus 1, and so on. In a moment, we're going to see that more in detail for the case of the fermionic systems. Okay. Now, so this was the answer for bosonic systems. Okay. And for example, by looking at this point of view, and that I guess came from these works, people realized that there were phases or systems with anomalies that went beyond the anomalies that you could get from group cohomology, like time reversal in 3+1 dimensions. Okay. I guess the anomalies was in 2+1 dimensions. Yeah. So now let's consider the same question for fermionic systems. So fermionic systems, just to define them, you have to choose a spin structure. Someone has to tell the fermions what to do when they go around an uncontractable loop in spacetime. So another thing that's important about fermionic systems is that they're endowed with an unbreakable Z2 symmetry that's generated by fermion parity. And that's what gives the Hilbert space a grading, and it splits into bosonic states and fermionic states. Okay? Now, classically, any symmetry G preserves fermion parity, which means that in the classical theory, -1 to the F commutes with any putative symmetry the system may have. Okay? This will be important later when we discuss anomalies. Okay? That's a statement of the classical theory, that G always commutes with -1 to the F. Okay? So now, what is the data? And by the way, this tells you that -1 to the F is a central element. -1 to the F commute with all other symmetries in the problem. Okay. So, having said that, now we can discuss what is the data that characterizes the symmetry of a fermionic system. So it's given by a group G. Okay. Now W1 is again the statement.
Question: what about supersymmetry?
Well, supersymmetry
does not commute with -1 to the F.
So Q doesn't commute, but the unitary transformation does commute, because you have like e to the I theta Q.
Okay, so when you say G, this is the group element. It's not the generator.
Yes, exactly.
Okay, thank you.
No problem.
I think, Jaume, you probably will make this point, but for fermionic, this invertible TQT or SPT, certain intrinsic fermionic generator, the boundary can have some different symmetry realization, such that the fermion parity does not commute with some additional boundary symmetry generator, right?
I'll get
you're told well. Yeah.
I'll get to that. Yeah.
Yeah. Thanks.
Good. So I already said what G was. W1 is just again a Wigner telling us whether the symmetry. We have to specify whether a given symmetry is unitary or anti-unitary. And W2 is a way of encapsulating the fact that this -1 to the F is central. It commutes with all group elements. So therefore, G essentially tells us that the full symmetry group of the problem, which is GF, is a Z2F central extension of some other group G. Equivalently, we can say that G is the quotient of the group of symmetries of the fermionic system modeled out by the central Z2F generated by Fermion number. Okay, so a very concrete example that's very important in condensed matter physics and also in particle physics, which is the symmetry we called it before Z4T. It's relevant for topological superconductors. Is when you have time reversal that squares to -1 to the F, and in this case, G is the Z2, and these two classes which live in Z2 are the non-trivial classes. Of the non-trivial W1 and W2 classes.
Jaume, I'm still puzzled by this -1 to the F and G commutator. So for you, G is the global symmetry element. So it's e to the I, alpha times the charge.
Yes.
Then whether it commutes with or does not, so that's, you say, will always be even?
Yes.
Okay, this is just a statement that every symmetry is a number.
Yes.
Okay, thank you.
Okay, so now let's discuss the classification of fermionic systems. Okay, so now, again, this was a lot of work that went into this. Another statement is that fermionic anomalies for a symmetry are classified by this twisted cobordism group, and the data is again the group and these two cocycles that I discussed. Okay. Now, so this is and computing this thing is really a mouthful. I mean, it's quite complicated. So I'm going to try to give you some physical intuition of one simple way as a physicist to think about this. Okay, so this twisted cobordism group is computable from a spectral sequence. Actually, there are several spectral sequences. The ones I'm going to describe is called the Hilbert spectral sequence. Okay, and if you read the idea is the following: is that you start with the naive answer that you would have guessed if you don't know any better, which is the group cohomology in d+1 dimensions. This would naively classify the SPT phases in d+1 dimensions. And then there are corrections that come at lower degrees. Okay, so with various Fanny coefficients. You see that here it's valued in G1, here it's valued in G2, G2, and Z. Okay, and the idea Hilbert spectral sequence is a machine that essentially allows you to compute what is twisted cobordism group given this data. Okay, and and essentially this, after a lot of work, this spits out what the answer for the classification of for the anomalies for a given symmetry. So here I wrote down the answer for important examples that we may discuss some of them later. So for example, let's look at anomalies in 0+1 dimensions for time reversal. Okay. So if you go through this procedure, what you find is that the anomalies have a Z8 classification. Notice that it is different than the naive classification because the naive classification would be that this would be given by H2 of Z2T, which is a Z2, not a Z8. Likewise, here, if you look at the unitary Z2 symmetry, the classification is a Z8 anomaly, while the naive answer would be again a Z2, and the same thing here for topological superconductors. The naive answer would be Z2, but now you get contributions from all the other layers. So the contributions from the effect of, I mean, these other cohomology groups, we're going to refer them to layers. Okay. Okay, so now let me try to give a heuristic interpretation of what's going on, what's the physical interpretation of these various layers. Okay. So let's do this. So an SPT has a symmetry G, and in particular, that means that it has a codimension 1 domain walls that implements the G action. Okay, so for every symmetry, there is a topological defect of codimension 1 that essentially, when it wraps on some object that's charged under it, it tells you what the transformation is. But now you can imagine that this domain wall can have junctions, and then can have junctions of junctions, and so on. So the basic idea behind this is that when you look at intersections of domain walls at various codimension, you have you can enrich that structure by stacking SPT with no symmetries on the various intersections. And so now, what are these lower dimensional SPTs with no symmetries that we have in fermionic systems? So these are well known, at least up to a certain dimension. So we know that in 0+1 dimensions, there is an SPT with no symmetry that has a Z2 classification. This is essentially the statement that you can have a gap quantum mechanical system, and the ground state can be either bosonic or fermionic. In 1+1T, there is a Z2 classification that's known as the Arv invariant. And in 2+1 dimensions, there is an integer classification, which is known as the P+AP superconductor. Okay, so these are the classification of SPT phases that where you have not imposed any symmetry. So the basic idea of this construction of the anomalies for the G symmetry is that when you look at the most general network of domain walls, you allow to stack with the right in the right intersection objects of these various dimensions. Okay? So in particular, so that's what I say here. So for example, we're going to stack a D-1 dimensional invertible theory on a domain wall junction. Or if you have a junction of a junction, you can stack a D-1 two-dimensional SPT phase. Okay. So now this gives a meaning to this. At least you can give a heuristic picture for what these various layers mean from the point of view of this network of domain wall intersections. Okay. So the first layer is just the bosonic layer, that's the naive answer. And then on the domain walls, you may be able to decorate by some Pli-Pli layer and in the intersections, you could have an ARF layer stacking it. In another codimension, you can have a psi layer depending on the dynamics. Okay. And the fact that that you have other objects living at the intersections, now what this does is modifies the usual pentagon-like identities that defined the original kind of Wedge-Dominic consistent condition. I told you what the anomaly was measured in terms of. They're corrected by things of lower degree, okay? And this corrects, if you wish, the answer from group cohomology to this cobordism group. Okay? So let me give you maybe very quickly, I don't know how much time. Yeah, very quickly an example, just so that it doesn't sound so crazy abstract. And I can draw some pictures. And I take the example in 1+1 dimension because that's as far as I know how to draw. So consider now the classification of anomalies for a unitary Z2 symmetry in 1+1 dimensions. There, the domain walls are implemented by topological lines. These are what codimension 1 is. And as I said, this tells you when an operator crosses the topological line, it tells you how it's transformed under that symmetry. Now, the domain walls can connect into junctions. So you have two elements, G1 and G2. They connect at the point and to another domain wall. Okay. Now, what is the statement about an anomaly in a bosonic system now? So, as I said, we can represent a G bundle. So, coupling your system to a Barkhan connection is the same as putting to your system a network of domain walls. Okay. And essentially, the statement of an anomaly is a statement that if I perform a gauge transformation, when I do a gauge transformation, I essentially am reconnecting domain walls. You're familiar with this, like in the Ising model, that you have the topological line that implements the usual Z2 symmetry of the Ising model. And by making a gauge transformation, I can move around that line. Okay. So the statement of that the system has an anomaly is that if I make a gauge transformation, the network can reconnect from the, say, the S channel to the T channel, but it can have a phase. Okay. And now the fact that you can concatenate these transformations, namely associativity, tells you it spits out precisely the statement that this nu3 is an element of the H3 group cohomology. Okay, that's one way of understanding where the classification in terms of group cohomology comes from. Just a statement that you have reconnection of networks, and then associativity constrains these phases. Okay, up to local counterterms. I didn't discuss about the local counterterms, but the local counterterms is what tells you that you live in H3. Okay. Now, how is this modified in a fermionic system? The first thing now is that the domain wall can have a Majorana zero mode attrapped to it. So I labeled this by nu1. So if you wish, you have the domain wall, which is one-dimensional, and on top of it, you can stack a fermion, essentially. So depending on whether you have a 0 or a 1, you have a fermion or don't have a fermion. Now, domain wall junction, and that fermion comes from the ARF layer that ends on the boundary of where the anomalous theory lives. Now, the domain wall junction also, it has this intersection point, and there you could have a fermion or not. So it's labeled by this Tuco cycle, nu2. And this could be thought of as the endpoint of the psi layer in 0+1 dimensions. So now, because you have these funny phases and fermions and blah, 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 when you do the associativity relations, like the pentagon identities, they're modified by this data. And this no longer tells you that, so here we said that for a bosonic system, nu3 had to be closed. Now, because of these signs, nu3 is not closed, and it's corrected by terms that come from the lower dimensional layers. And this is precisely the data that describes this cobordism group. Okay.
Can I ask a question now?
Yes, of course.
So what does it mean that the domain wall has a Majorana zero mode? I mean, I think of this domain wall as just some sort of artifact. If I want to couple the system to a gauge field, then this is just one of possible representations of the gauge field, this network, and I could have used different network.
Yes.
So
yeah, but
Majorana zero mode localized on the domain wall. The domain wall does not seem to be a physical object by itself.
No, in what sense it's not a physical object? It's a way of representing a G bundle.
So you are saying that I turn on the gauge field, and
turning on a gauge field is equivalent to turning on a network of domain walls. It's two different languages for the same thing.
So I think that there's a problem with terminology here. domain wall is often used when it is a dynamical object. And I think what you're talking here about is an interface. The interface is indeed what you just described. A domain wall is something that interpolates between two vectors of the system. So it is a dynamical object in the system. It can vibrate.
This is just the topological operator that implements the symmetry. What would be a better name for it? I thought domain wall was. I know that.
It's like an operator in the theory. So if it acts at fixed time, it's like an operator in the theory. It's not a domain wall. I think the issue is just terminology. I think that's what we're talking about.
Yes. So it's something that, if this is not clear, maybe we can discuss it later, because I should really move on to the next one. But essentially what I wanted to say is that in systems with fermions, you can see that the fact that you have low SPTs with no symmetries at various codimension correct the usual cohomological answer into something more sophisticated, which is this spin cobordism groups. Okay. So now, okay, so this was great. So now I think it's fair to say that we have a fairly complete understanding of what is the mathematical structure that classifies anomalies, both for bosonic systems and fermionic systems, for discrete and continuous symmetries and so on. But for a physicist, what I think that we really want to know is how do we detect whether an actual physical system has a 't Hooft anomaly or not? Because at the end of the day, it's great that we know the classification, but we want to know whether we can use 't Hooft anomaly matching constraints to tell something about the system. Okay, so of course the answer of how to detect whether a system has an anomaly is well known for symmetries that are connected to the identity. Sometimes these are called perturbative anomalies, and this can be detected as contact terms and correlation functions, and in many ways. And this essentially is captured by the free part of this spin cobordism group. Okay, but the real yes.
This is Max. Hello. Comment. I think you have to go to one higher dimension and then take the free part.
Yes, I think you're right. Yes. Yes. Thank you. Thank you.
But returning back, to this domain wall, I wonder, because in some low dimension you can have, a situation where your fermionic structure is, that situation is where you have not a state which have particular fermionic number, but it is a, the state which is combination of bosonic and fermionic. Okay, so where so it's not, and I believe that you are implying that it's not, it does not happen, right? So it's.
I'm not saying that. I think so. While you fault, I think what you're saying may be related to something I'm going to say very soon.
Say it again.
I think what you're saying is related to something I will say very soon. So why don't you hold your comment, and then if I don't answer it when I come to that, you can stop me again.
Okay. Sorry.
Yeah.
Thank you.
Yeah. So for perturbative anomalies, yeah. So let me correct this. That's great. Okay. So but what about for global anomalies? These are much more subtle things, and in particular includes anomalies for all discrete symmetries and the Witten anomaly, etc., etc. So in principle, I told you like the official answer to do this. You couple your system to G twist and spin structures if you know how to do that, and then you see how things transform as you make a background gauge transformation. But this is complicated, and actually sometimes it's not even clear how to do. Like for example, it's not really known in detail how to couple unoriented spin TQFTs, spin TQFTs to unoriented manifolds, stuff like that. So even setting up the problem of how to detect the anomaly is very subtle for global anomalies. And even when you can do that, and when an anomaly formula can be found, it's given in terms of really non-trivial data like the ATM variance in systems of fermions, or in bosonic systems where you can detect the anomaly. You have to use data like the F symbols of topological quantum field theories that can have anomalies. So essentially what we wanted to see is whether there was a kind of down-to-earth way to at least detect some of the anomalies by very elementary methods. And that's what I want to present. And what we will find is that there's a kind of a very naive thing that you can try to do. And this very naive thing actually is able to detect a surprisingly large number of anomalies. in various dimensions. Okay. So this is what I'm going to do now. So what I'm going to describe is an elementary method of detecting global anomalies. And essentially all that we will do is we will detect them by studying the Hilbert space of your putative anomalous theory on a flat torus, flat special torus. So we're going to use this exercise, just put the theory on the torus and try to study how, try to understand how the symmetries of your problem are realized on the Hilbert space of the theory on the torus. Okay. As I said before, the cohomologies are kind of built up by looking at contributions from various layers in these cobordism groups. And what we will find is that the various cohomology layers leave distinct anomalous imprints in the behavior of the symmetries in the Hilbert space. So different layers will have different characteristics in the way the symmetry is anomalous in the Hilbert space of the theory. Okay. And we will find that the severity of the anomaly in the Hilbert space decreases with increasing cohomology degree. And you will see in detail what I mean by that. Okay. Good. So since I don't know how much time I will tell you, but one of the things that will be important and that Jaume already mentioned is that certain anomalies, I already said that classically, minus one to the f is central, but it can happen that by virtue of a quantum anomaly, actually a symmetry G can become fermion odd in the Hilbert space. So instead of commuting with minus 1 to the f, actually on the Hilbert space it anti-commutes with minus 1 to the f. And this leads to a remarkable prediction for strongly coupled gauge theories. It essentially tells you that anomalous quantum field theories that have symmetries G that for which G becomes fermion odd in the Hilbert space have a supersymmetric spectrum of states. And the thing that's remarkable is that this is a non-trivial consequence of an anomaly, not of. I mean, we're familiar with the statement that you have both Fermi degeneracy when you have supersymmetry, but this is a statement that will follow from an anomaly and not from supersymmetry. And the thing that's nice is that so of course testing this is extremely hard because you know if you're looking at a strongly coupled problem, how are you going to know whether how are you going to test whether your system has a both Fermi degeneracy in the spectrum? But I mean, recent work, in particular in 2+1 dimensions, where there have been conjectures about what is the strong coupling dynamics of 2+1 dimensional gauge theories, by looking at the proposed answers that were given for the infrared dynamics of gauge theories, you can actually indeed show that the infrared theory that was predicted to appear has exactly both Fermi degeneracy. So this is kind of a very nice corollary of this is that you can use the statement that you have anomalies can lead to fermion odd symmetries on the Hilbert space, can give you information about the spectrum and predict the supersymmetric spectrum in quantum field theories, anomalous quantum field theories, Tufte anomalous quantum field theories. All right, so let me give you some intuition of what kind of anomalies can be detected and where you should be looking for them. Okay, so heuristically, we already discussed that anomaly is represented by a certain class that lives in this cobordism group. Okay. Now we're going to study the theory on a manifold, and since I'm a simple guy, I'm going to choose the simplest manifold, which is the torus. Okay. So now one thing you can think of doing is take this class and integrating it over the special manifold, a d-1 dimensional torus. Okay. And this spits out a class alpha 2 tilde. One way to think about this class alpha 2 tilde is that this is an effective anomaly class for a quantum theory in 0+1 dimensions. Okay. So essentially, now we can get an intuition about the anomalies by looking at the effective anomaly class of a 0+1 dimensional theory. Okay. Now, this point of view tells you immediately where you should be looking in the Hilbert space to detect anomalies. Now, if the torus, so usually when you study your theory on a manifold, you have to supply the manifold with certain structures. You have to give spin structures. If you have a background gauge field, you have to couple it to a background connection and so on. So this anomaly will be non-vanishing only in the Hilbert space with non-bounding spin structures. Non-bounding structures. What does this mean in practice? It means that if you choose your manifold, your torus, to have a certain structure, that torus has a non-bounding structure if this manifold cannot be the boundary of a one-dimensional higher manifold. If the structure of the torus is bounding, then this anomaly vanishes, essentially because you can represent this integral as an integral over one-dimensional higher manifold times d of alpha, but d of alpha is 0. Okay, so that tells us immediately that we're going to fish for anomalies by looking at the Hilbert space with non-bounding odd spin structures, like the Ramon spin structures, or we will have to consider Hilbert spaces with non-trivial holonomies for the global symmetry, like twisted Hilbert spaces. So you have the Hilbert space quantized in the background, where you have a non-trivial holonomy for a certain, say, Z2 connection around a circle. For these guys, the anomaly may or may not vanish, but at least there is no direct argument that it will be 0, while in the other ones, we know it will be 0.
Sorry, H is still the state space.
Sorry, go ahead.
Sorry.
Maybe Luke can go ahead, and then Nati can.
Okay. Sorry, so I just missed. Is H still the state space of this torus?
Sorry? Yeah, this will be the Hilbert space. So which H are you talking about, this H?
Yeah, for example, is it still the state space of the torus?
Well, so, okay, so this particular case, I just wrote, so this would be, for example, if you take a 1+1 dimensional anomalous theory, and you look on a circle, this would be the Hilbert space of the theory where on the circle you put Ramon or a non-bounding spin structure.
So we basically already reduced the problem to anomaly class in dimension 0 + 1, and then H is okay.
Effectively, but the point is that you have to be careful when you do it, because if depending on what structure you put on the torus, this will trivially integrate to 0, and you will have no chance of seeing anything.
Sure.
Okay? So the thing that's surprising is that here you can try to put certain non-bounding spin structures so that a priori this can be non-zero. And surprisingly, by doing this kind of very simple-minded thing, you can really detect a large number of anomalies by just doing this.
I see. Thanks.
Nati had a question, I think, or a comment.
So in one direction, it's completely obvious. Namely, if you detect an anomaly in this setup, it's clear that the full system has an anomaly.
Yes.
So my question is there any guarantee that this setup captures all possible anomalies?
No, absolutely not. No, absolutely not. This a priori will miss tons of anomalies. But the thing that's surprising is that it catches many of them. I mean, yeah. There is absolutely, I mean, that would be it would not be reasonable to expect that by studying the theory on the torus, you will detect all anomalies. That's definitely not something reasonable. Okay. Yeah. But the point I want to make is that you're able to detect much more than you would have naively thought by just doing something very simple-minded, like putting the theory on the torus. Let me mention that I mean, I guess I didn't really emphasize this, but imagine you want to study anomalies for time reversal symmetry. The official way of doing that is by putting them, coupling the theory to an unoriented manifold. Okay. Now, the thing that's surprising is that here you can detect large numbers of or a class of time reversal anomalies by just studying the theory on the flat torus. Okay. But of course, there is no reason to expect that this will capture all of them. Absolutely not. Yeah.
Jaume, one question?
Yes.
So are you going to tell us how do you integrate this alpha d+1 class?
No, because in general, I don't know how to do it. Someone more mathematically powerful should be able to take this data. You should be able to take this data, integrate it on a torus, and tell me what spits out. We haven't really done that. At a more general, I don't think people really know in detail, or maybe you can tell me how to do it, how to write the cobordism class explicitly in terms of this data. Like imagine I want to write the topological field theory action that describes the SPT given by some data like this. How do you write it in terms of this data? So no, we have not explicitly reduced the SPT to. But it can be done. I mean, I can give maybe since you asked, I can make a small parenthesis. I mean, this logic can be applied, by the way, to other manifolds. So let me give you an example on which the integral actually can be done. Even I can do it. Sorry,
one comment. I think just by the layers you're writing down, there's a naive way to pair the cohomology class with the bosonic cohomology class with fermionic a topological invariant that you list down by Poincaré dual. And then certainly you will come to that probably later. This the number of, like, say, the ZA class can be written as a linear combination of 1, 2, 4 with appropriate coefficient. And by that way, naively, you seems write it down, decompose the let's say the whole fermionic invariant, let's say ZA of Z16 class, boil down to some low dimensional fermionic invariant, and that stake Poincaré dual to this bosonic homology class gauge field. I don't know whether these are precisely mathematically rigorous, but at least computing suitable, manifold generators, you can reproduce a result. I think for physical purposes it's okay, but maybe mathematician can comment. I did write this in my paper that you can write this way. But anyway, you can come to that later when you have those terms.
I mean, I think one in principle can, there is no obstruction to taking these classes and integrating. One has to learn how to integrate over these classes over the manifolds. We have not really worried too much about it. Yeah, I was trying to make a comment that, I mean, by the same idea, for example, you can also consider other examples of anomalies like the SU2 with an anomaly. I'm going to give you an example of how this integration can give you immediately non-trivial information about, so this is the famous 3+1D SU2 with an anomaly for a fermion. So now here the cobordism class is essentially some one-dimensional class here, eta times C2 wedge F, okay? Now you can ask, and we can detect this anomaly by doing some eta invariant computation, quite sophisticated. Now, in the spirit of what I'm saying here, I can tell you a simple way in which you can try to fish out this anomaly in a very simple fashion. You can imagine, and it's not going to be by looking at the Hilbert space, but now you can consider this SPT and put it in a background on a force sphere with a background with instanton number 1. C2F is essentially instanton number 1, okay? Then the effective anomaly class you're going to get essentially is just eta, okay? But this is precisely the SPT class of the psi fermion. So this is the SPT class that tells you that you have with no symmetries, you have a fermion that's either bosonic or fermionic. This point of view immediately tells you that one way you can detect the SU2 with an anomaly is by essentially putting your system on a force sphere with an instanton background, and then this system will have an anomaly for -1 to the f. So -1 to the f will not satisfy the word identity, essentially because in the presence of an instanton background, you have a fermion zero modes, and then essentially you have a non-trivial one-point function for the fermion that violates -1 to the f symmetry.
Yes, it also tells you the S1 circle in the S1 times S4, this S1 cannot be bounded.
Yes.
Yeah, basically.
Yes. So this is just...
Wasn't that the original motivation for the anomaly? I think this was the original motivation, so that the instanton is only one fermion zero mode.
Or maybe it was. I do not know that whether in that work
I don't know if it was in so many words, but the fact that it was only one fermion zero mode was the motivation for that anomaly.
Yes, but this point of view now tells you very clearly that essentially the anomaly comes from the psi layer, the cobordism blah 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 story. Yeah. Okay. So I'm mentioning this just to say that it is in the same spirit, if you wish, in a similar spirit. You have some cobordism class that describes the anomaly, and you can integrate it over whatever you can and get something non-trivial out of it. Okay. Good. So essentially the problem reduced to some quantum mechanics problem. Let's try to study the anomalies as seen in the Hilbert space in 0+1 dimensions for the case of time reversal anomaly. Okay. So let's consider fermionic systems with a time reversal symmetry in 0+1 dimensions. And now here there are 3 layers. There is these 3 layers. Okay. And each one has a Z2. And I think this is what Jaume was saying. These Z2s actually compile when you go through this Atiyah Hirzebruch blah 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 story into a Z8. So nu is an integer mod 8, and the layer contribution can be given by this. Okay. So essentially the ARF layer tells you corresponds to the values of nu that are odd. the psi layer, the values of nu that are 2 mod 4, and the bosonic layer is 4 mod 8. Okay. So now what I want to do is something that's extremely simple, and we will see that this will repeat over and over when we go to higher dimensions. We want to understand how the symmetries of the problem, essentially time reversal and -1 to the f, are imprinted in the Hilbert space of the system. And one very concrete way to study this is by considering anomalies in a system of new fermions, which have this usual action. Okay. Now, the system realizes precisely the symmetry that we want. It has a time reversal symmetry that acts this way, and it has a -1 to the f, z to f that tells you that the fermions are fermion odd. Now it's well known, especially by Kitaev and other people, that this system you can add a Z2 symmetric quartic interaction that gaps 8 fermions. So we can just essentially consider a system where nu is an integer from 0 to 8 to 7. Okay, good. Now, so now we want to ask. So now let's do the following exercise. Let's study the Hilbert space of this theory and try to see how the symmetries are realized. So we want to know what happened to 2 squared equals 1, and what happened to the classical relation that t commutes with -1 to the f. Okay. So these are symmetries of the classical theory, and these are relations that are obeyed by all operators in the theory. Now we want to see what happens in the Hilbert space. So let me tell you what the answer is, and then if I have time, I'll tell you a few words. I mean, deriving this is extremely elementary. So how are these anomalies realized in the Hilbert space? So let's start with nu equals odd. So as I said, this comes from the RF layer, the smallest layer. And the way you can detect that is by the most severe anomaly. Essentially, the statement is that when nu is odd, the theory does not even have a graded Hilbert space. Remember that I said in a fermionic theory, the Hilbert space should be graded. It should have a bosonic part and a fermionic part. And when nu is odd, essentially, there is no action of -1 to the f that on the Hilbert space. So the system does not even have a graded Hilbert space. Okay, so that's one way of thinking of detecting the anomaly coming from the RF layer, as saying that there is no graded Hilbert space. When nu equals 2 mod 4, we do have a graded Hilbert space, but now all of a sudden the time reversal, which was classically fermion even, now becomes fermion odd when it acts on the Hilbert space. Okay, so that's another manifestation of that you have an anomaly when for these values of nu in the Z classification. Nu t all of a sudden has become fermion odd. Okay, and finally the last. And this comes from the psi layer. Okay, and now let's go back to the last layer. In this case, when nu equals nu 4 mod 8, we have a great Hilbert space. T is fermion even, but now t squared acting on the Hilbert space is -1. So in the last layer, Z2T is realized projectively on the Hilbert space, which is what you would expect from the bosonic layer. Okay, so this essentially tells you how the different layers leave an imprint as different manifestations in the Hilbert space. And now to prove this is very elementary. Before I do that, so this leads immediately to a following lemma that you can prove. It tells you that eigenstates in any Z2 symmetric anomalous theory are degenerate. And it doesn't have to be free fermions. You can add like SYK interactions, you can add scalar fields with Yukawa couplings, blah, blah, blah. If nu equals 4 mod 8, it tells you that it's essentially the statement of Kramer's theorem that you have degeneracies. And when nu equals 2 mod 4, because for nu equals 2 mod 4 t and they commute with -1 to the f, what you find is that the degenerate states have opposite fermion parity and therefore a supersymmetric spectrum. And that's something that in the context of 0+1 dimensions was already noted by these authors and probably more. Okay. Now, how did we prove this? This is elementary. All you do is canonical quantization of the fermions, and essentially the Hilbert space gives you a representation of a rank nu Clifford algebra. Okay, the statement that the anomaly is Z8 is just the statement, the mathematical statement that there is both periodicity of Clifford algebras mod 8. Okay. Now, how do we conclude that for no odd there is no graded Hilbert space? Essentially, the point is that for no odd there is no operator on the Hilbert space that anticommutes with all the gamma matrices. Okay, and that's just a statement there is no graded Hilbert space. From the partition function point of view, if you compute the partition function of the theory, you find that when nu is odd, it doesn't have an integral expansion. That's just, I mean, a more path integral way of saying that the theory does not have a graded Hilbert space. Okay. And when nu is even, you can just construct explicitly the Hilbert space by introducing creation and annihilation operators with the fermions.
Sorry, I have a question here. So when nu is odd, would you say that there's just no Hilbert space at all, or no gradient?
These are words. These are words. I mean, there is a Hilbert space. I mean, there is the spinor representation of.
But the number of states is an irrational number.
There is a Okay, so there is a representation of psi A as matrices, but there is simply not there is no operator that anticommutes with all of them. That's what we're saying. Another way of saying it is that if you look at the Ramond sector, the -1 to the f word identities are violated. Essentially because, that's another way of saying that all of this, that if in the Ramond sector, the 1-point function or say for nu equals 1, the 1-point function of a fermion in the Ramond sector is non-zero, but this violates -1 to the f symmetry.
But I believe it is a case I was trying to ask about, because in situation when you have, you know, this -1 to the power f violation, it okay, in particular example, it implies that your Hilbert space is split into two, and in which one, you know, your state is combination of bosonic and fermionic. So, but there is a kind of super selection between two sectors. So you are, if you are taking one that -1 to the power f violated because your states is combination of fermionic and bosonic. Okay, and you know, in one Hilbert space is the sum of this fermion and boson, and another one is say difference between boson and fermion. Okay, so you still have.
I think what you're saying can be said in the following way, that for no odd there are two irreducible, there are two inequivalent spinor representations.
Yeah, right. And
-1 to the f maps one to the other. That's what you're saying.
Yeah.
Yeah, but
right, but it is still kind of example of, say, like king in 1 + 1 dimension realizes this in explicit form. You know, I mean, this situation.
Yeah, but I would definitely call that an anomaly. The -1 to the f word identities are violated.
Yeah, right. But there is nothing wrong with the series still itself. So you still
Tuft anomalies are things to be treasured, not there.
Yeah. Okay.
My question is, z, the partition function is not an integer when nu is odd.
Right.
Doesn't the partition function computes the number of state in the Hilbert?
Well, that's the whole point. It doesn't. If there is no Hilbert space, if there is no proper Hilbert space, it doesn't.
No. When you account for this,
there is no Hilbert space in this case, right?
No. When you account for the fact that Hilbert space is split into two, then the number is okay, because the point is that how many kings you have in this situation, and the statement is that you have not two kings in spite of the fact that you have fermions, because there is no -1 to the power f. So you in each sub Hilbert space you have just one state. Okay, so z in this sense would be okay, but this should be defined in correspondence with this.
I think it's a matter of interpretation. I think the thing that's unambiguous is the -1 to the f word identities are violated, and I would call that an anomaly. So
it's an anomaly, but this statement that this kind of square root of 2, say, number of states is related to what I was trying to say.
Yes. Okay, yes. So, and now to conclude the rest.
I'm still puzzled by that. So, first of all, you use anomaly. Sometimes anomalies mean that the theory is inconsistent, and sometimes you use anomaly to say that there's an 't-Hooft anomaly.
Yes.
And the terminology is unfortunately confusing.
Yes. I'm only talking about
saying that the case of nu odd is like an 't-Hooft anomaly, namely the theory makes sense in the theory, that there's a problem with the symmetry in some correlation functions, or are you saying that the theory doesn't make any sense when nu is odd?
No, I'm saying the first, that
what are you saying?
I'm saying that the theory makes sense, it's just the word identities are violated for a symmetry.
But then you really have to address Shuheng's point. How many states are there in the Hilbert space?
Well, so I mean, depends on well, I mean, they don't have a canonical Hilbert space interpretation, but I can write down the correlation functions of any theory, and they will satisfy whatever properties they have to satisfy, except that they violate the word identities.
So, for example, in this case, you could just, let's say nu is 1. Can you just double the Hilbert space and say that there are 2 states and then everything is perfect, or not?
Well, then you would have to add the other spinor. I mean, you can choose to add the other spinor representation.
Well, there's a question of, is the anomaly a disease or is it the property of the theory? And for nu equal 1, or more generally for nu odd, it's not clear to me which of the 2 you're saying.
I would say that there is, I mean, depends what wrong means. I mean, it doesn't have a graded Hilbert space. If you consider that that's something you cannot live with, then I would say that then there's something wrong with it.
No, as it stands, according to this slide, I would say that the theory doesn't make any sense because it has root 2 states.
Yeah. Yeah, so that's why I said that it's if you wish, it's the most severe type of anomaly. But I think it's still, so even though it doesn't have a proper Hilbert space interpretation, you can still discuss its correlation functions.
Oh, by the way, I think maybe I can say something. Just there are consensus in condensed matter theory. So the condensed matter folklore now is saying that the R case is a problem for the boundary, this theory living on the boundary of some invertible fermionic topological order. And that bulk state, the 1+1D bulk state, is the well-known Kitaev chain, but it should be understood as not SPT protected by protected by symmetry, but just fermionic intrinsic invertible topological order, which is long-range entangled. So if you want to cancel these type of things by some other theory, then you better to cancel this long-range entangled things in the bulk to some additional long-range entangled things. And one strategy will be done by Dagoff and Witten in 2018, the topological gravity story that he had. But other than that, there's no other QFT that is well defined, in my opinion, to cancel the anomaly. And for the nu even case, basically these are indeed Tahu anomaly for the fermion parity symmetry of the spin greatest, the rotational symmetry was the Z2T, that symmetry, the P minus structure. And that one indeed is a Tahu anomaly. They can be understood as a boundary anomaly of some boundary theory of some 1+1D dimensional bulk fermionic SPD, which is short range entangled. I think that's consensus in condensed matter. And anyway, so that's what I can say.
Yeah. Okay, so maybe with the time is running short, let me move quickly to some other example in higher dimensions. And so I guess I'll be quick with that because I'm running out of time, and then discuss something more in 2+1 dimensions. But let me tell you another case that has the flavor of this, which is in higher dimensions. So let's consider now 1+1 dimensional theory with a unitary Z2 symmetry. This theory have a Z8 anomaly also that comes from these various layers again. Okay, and the anomaly has this kind of binary expansion. One way we can detect anomalies in the Hilbert space is by studying the Hilbert space of nu Majorana fermions. Okay, where they have this Z2 symmetry is a chiral symmetry that negates the left moving fermions, and then you have, of course, the usual fermion number symmetry. Okay. Now you can just quantize the theory, and you will find the usual canonical commutation relation. Okay. Now let's construct the Hilbert space. So now it goes back to the issue of what Hilbert spaces we should be looking at. There are several Hilbert spaces we can consider. We can consider, so we have the theory on a circle, And we can either consider the Hilbert space with Neves-Schwarz or Ramon boundary conditions, or we can turn non-trivial holonomy around the circle and define what we would call a twisted Hilbert space. Okay. And we should study how the symmetries are realized in all these Hilbert spaces. But we already know from what I said before, the general argument, that we will only be able to see an anomaly or a problem when we consider non-bounding structures on the circle. So that tells us that either we will have to look at the Ramon Hilbert space or look at the twisted Hilbert spaces, which cannot be extended. Okay. Now, how are the anomalies seen? The anomalies are seen essentially in the way the symmetry is realized on the zero modes in the Ramon Hilbert space, which is non-bounding, and on the twisted Hilbert spaces of the theory. Okay. You can read our view from. Okay.
Forget about this. These are just comments for others.
Okay. So now again, this will be similar. So if you now look at the twisted Hilbert, so there are two ways of detecting the lowest layer. So by looking at the twisted Hilbert space, essentially you again find that there is no -1 to the f, essentially because again you have an odd number of zero modes. In the twisted Hilbert space, the left moving fermions and the right moving fermions have opposite boundary conditions. So you only have zero modes for, say, the left moving sectors. And if nu is odd, you get an odd number of fermion zero modes. And therefore, the partition function, that the theory does not have violates -1 to the f word identities. Instead, if you decide to look at the Hilbert space in the untwisted Hilbert space, but in the Ramon spin structure, what you find is that in the Hilbert space, now -1 to the f left, all of a sudden anticommutes with the fermion number. Okay. So that's very similar to what I said in 1 + 1 dimension, where this layer is detected by virtue of the fact that now the symmetry becomes fermion odd. Okay. Maybe I was going to say that you can detect other layers by other values of nu by doing other things, but by virtue of time, I will just move on and go to the. Okay, and just make a couple of comments here. Okay. So very similar to what I said in 0 + 1 dimensions, the fact that for nu odd -1 to the f left becomes fermion odd tells you immediately that theories that have again, now this can be interacting theories, it can be 1 + 1 dimensional gauge theory with Yukawa couplings, whatever you want. The theories that have an odd nu anomaly will have a supersymmetric spectrum. So in particular, if you take SUN adjoint QCD for n even, you will find, well, the prediction is that this theory will have a supersymmetric spectrum in the Ramon sector. And this is also something that was noted and shown by doing a circle reduction by these authors. But then this can be generalized to many other interesting theories, where the fact that you have a Z2 symmetry with an anomaly with nu odd tells you that this theory must have a supersymmetric spectrum. Okay? So that's kind of another interesting example of how anomalies predict something non-trivial about the spectrum of the theory.
Jaume, question. It's only on the torus, right?
I'm always on the circle. Yes. Yes, on the torus. Yes. Okay, so now let me tell perhaps the richest case.
Jaume, can I ask a quick question?
Sure.
Sorry. So what happens to this Bose-Fermi stuff on R2? Do you have any comments? Like, what are the bosonic and fermionic states that become related? Is there anything one can say?
I don't have something very specific to say, no.
Right, so that, okay.
No, so I'm talking about the supersymmetric spectrum on the torus, always. Yeah. So now let's consider the case of topological superconductor symmetry. Theories in 2 + 1 dimensions that have a time reversal anomaly of this type. Now, in this case, we have 4 different layers. And again, the different layers come from this binary expansion. Okay. Now, this setup is extremely interesting because these systems, you can consider systems that have this symmetry and these anomalies by studying fermions, but also non-trivial topological quantum field theories. So that's the natural home of topological quantum field theories 2 + 1 dimensions. And both systems can have these symmetries and these Tuft anomalies. Okay. And now you can do the following thing. You can say, okay, let me try to study the Hilbert space of these theories and see how the anomaly is represented on the Hilbert space. Okay, and you can do it both for fermions and topological field theories. And let me just tell you what the answer is, and then I may say something about spin TQFTs that one needs to develop a bit further to really answer this question. Okay, so what we do is study the Hilbert space of 2 plus 1 dimensional systems on a 2 torus. And now you have to, and there are now 4 different Hilbert spaces. You have to specify the spin structure along the 2 circles of the torus. Okay. So what do we find by studying the Hilbert space both for fermions and spin TQFTs? We find that for new odd, when the anomaly is odd, T all of a sudden becomes a fermion parity odd in the Ramon-Ramon sector, and it's parity even in otherwise. And this can be represented by this equation where ARF is essentially what's known the ARF invariant, which is +1 for even spin structures and -1 for the odd Ramon-Ramon spin structure. So it's commuting for even spin structures and anti-commuting for odd spin structures. While for nu equals 2 mod 4, Z4T is realized projectively on the Hilbert space and vectorially otherwise. And again, this can be represented by this equation where on the Hilbert space, the symmetry is not realized as T squared equals -1 to the F, but there's a correction due to the ARF that picks up a minus sign in the Ramon-Ramon sector. So this is an example in which you could detect time reversal anomaly, which you would putatively would have to study on an unoriented manifold to really see the whole thing. But that you can fish parts of it by just studying the theory on the Hilbert space, on the torus, and seeing how they leave imprints on how the symmetries are realized there, essentially. So in the last couple of minutes, I will just maybe say a couple of things of how this is done. I talked a lot about fermions. I want to say a couple of words about how this is done for spin TQFTs. I mean, I think to do justice to this, that would require a talk on its own. So I'll just say a few simple things. And I'm just saying this in case people are interested.
Jaume, by the way, take your time, no rush. Take your time.
Really? Okay.
Yeah, take your time.
Okay, so I'll just say a few things of how you would construct the Hilbert space of a spin TQFTs and how you would compute whatever you need to compute to detect the anomalies there. Okay, from this, at least from this simple-minded point of view. So what is a spin TQFT? It's a topological field theory that depends on spin structures, like fermions do, and where the Hilbert space are graded. You have, again, bosonic and fermionic states. And there has been a lot of work on them, but we had to go a bit beyond what was known in the literature to really complete this problem. So what one way to think about spin TQFTs? One way to think about it is that you can, so a spin TQFT has a -1 to the F symmetry, just fermion number. And what you can do is essentially sum over spin structures to produce an object that does not depend on a spin structure, which is a bosonic TQFT. It's known that if you get the theory by gauging, you can go back by essentially gauging a dual symmetry. Mathematically, it's a statement that the Fourier transform has an inverse. Okay, so you can go in this way or you can go in this other way. Okay, so one way that we will use concretely to define spin TQFTs is by studying with a bosonic TQFT with a certain property and then gauge a particular Z2 one-form symmetry that's generated by a fermion. Okay, so that's one way in which you can concretely define how to compute the properties of a spin TQFT. Okay, now and the way you construct is by studying with the bosonic theory and gauging this one-form symmetry, which in the condensed matter literature is sometimes known also as fermionic anion condensation. Okay, and by doing this process, we can construct various Hilbert spaces in the 2 torus, and there are several sectors. You can have, again, you have to choose a spin structure on each of the circles of the torus. So now we have to understand what is the Hilbert space of a spin TQFTs on the torus. If the theory is bosonic, we know that the Hilbert space of a bosonic TQFT is given by the space of conformal blocks on the 2 torus. In this setup, the space of conformal blocks of a spin TQFT is given by the space of conformal blocks on the 2 torus and the once puncture torus, which I represent in this picture. So the Hilbert space is done by inserting a line along, say, the B cycle of the torus, and But in a spin TQFT, you can also get states from the one-point conformal blocks in the bosonic theory. Okay, and I represent the conformal blocks by this skeleton picture of the torus and the once-punctured torus. Okay. By the way, there's some lines that I cannot see. Okay. So that's how you construct the Hilbert space of the theory. And what we want to know is how to compute the action of operators on this Hilbert space. And this Hilbert space have to give a representation of the modular S and T matrices, which furnishes a representation of the double cover of what's called the metaplectic group, which is a double cover of the modular group. Okay. So now we can explicitly construct the Hilbert space of the spin TQFT in the various sectors. And essentially it's given by, in the even spin structure sector, is essentially given by inserting various lines on the B cycle of the torus and with various linear combinations of this, in this way. Okay. Something new happens when you're in the Ramon sector, because you can construct states where essentially because the bosonic theory may have states M that have fused when they fuse with the fermion that you're gauging or condensing gives you back M. Okay, so yeah, I'm being a bit fast with this. So essentially, the Hilbert space of the even spin structure is something that you would know how to do essentially just from the usual conformal blocks of the bosonic theory. And in the fermionic case, you have to be careful that since you're gauging the fermion, you can consider conformal blocks where you have an external line, which is a fermion. Okay, and the thing that's important to say is that how to read the fermion number of the various states in the Hilbert space. And the point is that the states that just come from the torus are bosonic, and the states that come from the one punctured torus are fermion odd. They're fermions. Okay, and the reason is that -1 to the f measures essentially the fact that you have a puncture on the torus. And then you can compute the action of the operators, which are essentially the Wilson lines that are labeled by the anions of your theory in the usual way. So if you consider a Wilson line labeled by anion A wrapped around the A cycle of the torus, the state is computed essentially by the modular S matrix. If you insert the Wilson line labeled by anion A on cycle B, you compute the matrix element by diffusion. And here is something that's more non-trivial. If you want to compute the action of matrix elements of the Wilson lines on the states created on the one punctured torus, you have to use the F symbols of the bosonic parent theory. Okay, so that's something that we had to work out. That essentially you can compute the matrix elements of all states, but you may need more sophisticated data of the bosonic parent theory than just the modular data. You need, in particular, the F symbols. Okay, so now I can just tell you a few examples or give you a flavor of what we did.
Jaume?
Yes.
About the previous two slides, are you kind of explaining how to ungauge this bosonic theory? Is this how I should?
I'm telling you how to construct the Hilbert space, the matrix, essentially how to construct the Hilbert space, the matrix elements of operators, and the modular data of the spin TQST from data of the bosonic parent. And what I'm saying is that in order to construct the data, you need to go beyond the modular data of the bosonic theory. You need to add more. You need to know more about the bosonic parent theory than just the modular data.
Got it. Thank you.
Yeah. So to do justice, this should be a talk on their own. But anyway, I just want to give you a flavor in case it's interesting. So something that was realized in the last few years is that Chern-Simons theory can actually be non-trivially time reversal invariant. That's something that perhaps is surprising because Chern-Simons theories are typically the prototype example of theories that are that break time reversal. And there are many families of examples here. I listed a few of them, like SON level n, UN level 2n, and so on and so on. You can also do it for theories U1 level k. I mean, the simplest Chern-Simons theory can also have a time reversal symmetry if the level k satisfies certain arithmetic properties that are interesting. Okay. Now, how do we know that the theory has a time reversal symmetry? Well, we know because the time reversal acts non-trivially permuting the anion. So it changes any anion in the theory to some image anion it preserves the QFT data. It reverses the spin, it preserves the S matrix up to complex conjugation, blah, 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 blah. Okay. So the way we can detect the anomalies for time reversal in this theory is in the following way. I already told you quickly how to construct the Hilbert space of spin QFTs in general. I told you how to construct the matrix elements of the Wilson lines labeled by the anions. So the way we can detect the anomalies is that we can explicitly construct T, the time reversal operator, when it acts on the Hilbert space. And we know that T should map the Wilson line to labeled by anion A to a Wilson line labeled by the image of the anion A under time reversal. Okay. And when you do this exercise, you indeed find, again, this is cut for some reason, I don't know why. What you find is that time reversal, indeed, as I advertised, becomes fermion odd when nu is odd and becomes projective when nu equals 2 mod 4. Okay. So this is a very concrete way of exhibiting the time reversal anomaly just by looking at the implementation of time reversal on the Hilbert space of the spin QFT. Okay. So here, I was going to give a trivial example of SO3 level 3, but let me not do that. Yeah. So now let me give you a lemma of this I think it's fun. So again, now I want to use the fact that for a particular value of nu, for nu odd, if a system has a Z2 symmetric, Z4 symmetric, it can be any gauge theory that preserves Z4 symmetry, and the anomaly is odd, then the theory must have a supersymmetric spectrum. Okay. Now this is of course hard to compute because we don't know how to solve 2 + 1 dimensional gauge theories because they're strongly coupled in infrared. Okay. But recently, the infrared dynamics of such gauge theories have been put forward and shown, or at least conjectured, to have interesting novel quantum phases that can appear in the deep infrared with emergent anions, emergent gauge group, emergent gauge fields, and so on. In particular, let me give you an example of a theory where we will be able to use this lemma. Okay. So take an SON gauge Young-Mills theory with a quark in the rank 2 symmetric representation. Okay. Now this theory is time reversal symmetric if n is even, and it has a odd anomaly when nu n equals 0 mod 4. Okay. Now it was conjectured that this theory in the deep infrared, I mean by a series of complicated arguments including anomaly matching, that this theory flows in the deep infrared to this particular time reversal symmetric Chern-Simons theory. Okay. Now, since this theory has no odd, one of the things that has to be true is that the spectrum is supersymmetric. Okay, so one way now you can go ahead and do, which we did with Diego in some other paper, is you can compute the Hilbert space and the torus of this particular time reversal symmetric Chern-Simons theory. Okay, so a more general one. So SO odd with odd level. And again, doing this is a bit of a complicated exercise. You need to essentially count how many states in the Hilbert space are bosonic and how many states are fermionic. Okay, so that's something that you can do, and you find that the number of bosonic states is this and the number of fermionic states is this. But notice that precisely when n equals k, which is what you predict here, the theory should flow. The theory indeed has exact Bose-Fermi degeneracy. So this is one of the few examples in which this kind of non-perturbative prediction about the behavior of the spectrum at long distances can be reproduced, albeit by this conjecture. So this is of course not proven, this is a conjecture, but this conjecture is consistent with the fact that the spectrum of this theory should be Bose-Fermi degenerate. Okay. So let me just conclude. So what we've seen is that some global anomalies can be diagnosed in a very simple fashion by studying the Hilbert space. Different layers leave different anomalous imprints in the Hilbert space. And perhaps very interesting is that these anomalies imply out of the blue that the theories with the right set of anomalies must have a supersymmetric spectrum. Along the way, even though I didn't do justice to the subject, one has to go deeper into understanding spin QFTs. And I think that's interesting. I mean, and I think that is fun is that we're still kind of learning and uncovering interesting facts about quantum field theories and anomalies. So with that, I'll stop and I'll thank you for your attention. Thank you.
Thank you, Jaume. Muchas gracias por su seminario. Questions from the audience? Feel free. I think Nati probably already have a question. Nati?
If you insist, you could generalize that to either added manifolds or or putting defects and looking for the realization of the system there. And I know that some people conjecture that if you study it on all manifolds with all defects, then, but it's just quantum mechanics. In the end of the day, just quantum mechanics by reducing the theory on some manifold, perhaps in the presence of defects, this would probe all possible anomalies. Do you have any view on that?
It sounds reasonable, but indeed, yes. I mean, if you allow yourself all possible manifolds and all possible defects, I think essentially it's going back to a way of representing the mathematical underpinnings of the cobordism construction. Well, I think that should be true. I can say something more concrete. I mean, this example, I consider the Hilbert space of the TQFT on the torus. But actually, even though we don't know how to do it in detail, you could say, can I see some other layer by considering the theory on the Klein bottle, for example? And I think the answer is yes. So if you're able to study the Hilbert space of the theory on the Klein bottle, you're able to see another layer of the anomaly. So indeed, if you are able to construct the Hilbert space on all possible manifolds with all possible defects, it seems not impossible that you will be able to see everything. But I am very surprised that the torus sees as much as it does. So, for example, this thing that you said, is it known how to do it for the Witten anomaly? For example, if you put the theory on which three manifolds, which three manifolds you should study the Hilbert space and which defects to see the anomaly?
I think that's what you said. There's an odd number of Fermion zero modes.
No, but I detected it not by studying the Hilbert space. I detected it by going to the force sphere and turning on an instanton background.
I think we're again careless about the terminology. The Witten anomaly makes the theory inconsistent. It's not an approved anomaly.
I guess it's a global symmetry.
I think of the SU2 as a global symmetry. I'm not gauging it.
Ah, okay. So it's a system with a global SU2 symmetry.
Yeah. I'm never gauging anomalous things.
So it's the same thing. You turn on background field for the SU2, which would be one instanton, and then. But I do not know how to do that in Hamiltonian formulas.
Well, that's my question. So I guess the question to me is whether that anomaly can be seen by choosing studying the Hilbert space on a three manifold with suitable SU2 bundle, suitable SU2 bundles turned on. And I think you're saying that the answer should be yes, right?
Yeah, but I'm trying to follow up. I mean, Nati, I believe that I agree with you that in the case of Witten anomaly, you would say that the theory doesn't exist, right?
No, but again, when I said that, by Witten anomaly, I'm not gauging the SU2. It's a global symmetry.
I see. Okay, but the theory in gauge theory with this SU2 anomaly, is not consistent by itself.
Again, it is consistent if the SU2 is a global symmetry. It becomes inconsistent the minute you gauge it.
Yeah. Okay. Thank you.
No problem.
I wanted to make a comment on the question before you asked if you're given a collection of these cohomology classes, how you can create or whether you can create this Bordism invariant.
Yes.
Yeah. So this is a very hard problem because of a couple of reasons. I mean, first of all, you cannot just take, of course, an arbitrary collection of cohomology classes because there are these constraints, right, coming from a spectral sequence.
Yeah.
So there is some non-trivial condition that you need to impose, otherwise the invariant is not going to be well defined for some reason. But the bigger problem is that you have these extensions. So for example, for the case you considered before of the time reversal symmetric Kitaev chain with t² = -1. you have these 3 Z2s, right, that combine to give a Z8.
Yeah.
And what you could try to do is what Jaume just said, is you can do some construction with taking Poincare duals of things. You can get some invariants out of those, but they are not going to be defined for all manifolds. So for example, one of the Z2s is exactly the ARF invariant, right?
Yeah.
But the ARF invariant is only defined if your manifold is actually spin,
right,
and not if it's unorientable. So the situation is that you have these 3 Z2s give you 3 invariants,
yes,
and like one of them gives you a well-defined invariant, and if that one vanishes, you can define the next invariant, which is the next Z2, and if that one vanishes,
right,
then you can define the next one.
Right.
So that's the situation.
Yes, I agree. But I think there should be a way of more explicitly being able to take the data and with all the constraints. I mean, the reduced data, once you go to quantum mechanics, should obey the constraints that the cobordism group in 2 dimensions must obey. And one should learn how to do this. Well, someone should learn how to do this properly. Well, I mean, I have not seen people doing that. Yeah.
You're right. It would be really interesting.
Yeah.
Let me ask a question. So you discussed supersymmetric both Fermi degenerate spectrum for certain Tahu anomalous theory.
Yes.
The theory was Tahu anomaly. So
sorry, just with a very specific, not any anomaly. It has to be like no odd.
Yeah, I know for certain Tahu anomaly, there is some both Fermi degeneracy in supersymmetric spectrum. And my question is that how this spectrum can help us to maybe deform the theory to some supersymmetric field theory or supersymmetric gauge theory. Is this does this original?
I mean, having a supersymmetric spectrum doesn't say that the theory. Right. I mean, you can tell you that the theory is supersymmetric in any way.
Right. So I say that because
this theory is very far. This theory is very far from being supersymmetric.
Okay. But is there maybe some deformation, maybe some paths that something we can engineer?
Oh, you're saying that if I can
we do something to make that, since we already have a supersymmetric spectrum, maybe is there some thought on how do we deform the theory to
that's a good question,
theory that we can probably have more control and do things that
So this goes back to the comment I said that, I mean, in principle, I can add degrees of freedom that are preserve the symmetry.
Yeah.
And the anomaly should not change.
Yeah, that's right.
So whether I can do that and go to, if there is a path that I can go to a supersymmetric theory, that doesn't sound impossible. I mean, right now I don't see an obvious no-go. That's a good point. That's possible.
Yes. Yes.
Can I ask a question?
Please.
Sure.
Yes. So you had a picture. Yes, on the previous slide. Yes, for example, this one with a line coming in and a circle after that. In terms of the 2+1D TQFT, in which we're gauging this symmetry, is it supposed to be a junction of lines?
No. Okay. Well, yes and no. I mean, let me go to this picture. I think this picture will be more helpful. Essentially, okay. So maybe I should tell a little bit why is this happening. Essentially, we're gauging the psi anion to work from here to here, right? Yeah. So I tell you that essentially, psi in the gauge theory is indistinguishable from the vacuum. So that means that I should consider all torus conformal blocks with psi insertions. Okay. So what is this picture? This picture is just the usual. So if you forget about the puncture, psi puncture, this is the usual way in which you can construct the Hilbert space of Chern-Simons theories. You insert a line along a circle, and the psi is just studying the Hilbert space in the sector where you have a line in the time direction, the psi line in the time direction, essentially.
Yeah.
You can think of that. Yeah, you can think of it as a network. If that helps, yes.
Oh, so we can think of it as a junction between two lines, psi and m.
It's a junction that has, and these guys are called Majorana lines. And they have the property that they can absorb or emit a fermion. So you have a junction with psi and m, and you can only have them, of course, for anions where this fusion is obeyed. Otherwise, you cannot even write down the conformal block.
So is it fair to say that in the theory, in the theory obtained after gauging psi, we get a line that is that should be thought of as this junction line junction of lines in the original theory?
I mean, this is the picture in the original theory.
Right,
So
but does this correspond to sort of a line in the new theory?
Well,
the gauge theory, or no?
Psi doesn't really exist in the new theory in some sense. You've gauged it.
Psi does not, but does this sort of a configuration have a physical meaning? It's giving us a state.
Yes.
So does this configuration, should it be thought of as a new line in the gauge theory?
I wouldn't use those words, no.
Okay. I think my confusion is coming from the fact that that when we do like just bosonic, when we gauge bosonic one-form symmetry,
yeah,
then we get for a line that is like a fixed point under fusion, for example, the one that's M here, then we get two lines in the the gauge theory.
Yeah. So something that's very, very different here. Oh shit, this kept disappearing. Okay. Something that's very different in the bosonic anion condensation and fermionic anion condensation is that in fermionic anion condensation, there are never multiplicities of fixed points. Why are there multiplicity in the bosonic case? Because essentially what it says is that the fixed line under the condensed anion is in the regular representation of some symmetry, and that splits into irreducible representations of that symmetry.
Yeah.
But here, we're in a gridded Hilbert space, and the point is that the representation you get is the Cliff 1-1 representation, and that's irreducible. So each fixed point gives rise to one line, not multiplicities. That's one very important difference between bosonic and fermionic anion condensation.
Okay, I see. One more question that I have is that when we say that we are going to put Majorana zero modes on top of a symmetry generator domain wall, how do we think about it in terms of the bundle, G bundle, mathematically? Like at a mathematical level, do you know how to say it?
I mean, all I can say is that mathematically, a G bundle is essentially the same as a network of topological defects. I think that's something that mathematicians would agree. And what we're doing is enriching the bundle with extra structure. So,
right, but what is that structure mathematically? Like these Majorana zero modes, putting them on mathematically, what is that structure?
I'm not sure what the word is. Maybe someone knows what the right mathematical words that go with it are. I think it's like a twisted G bundle. I mean,
probably twist the spin or pin with other internal global symmetry G. There's a twist structure between the two things.
Okay, I see. So in 2+1D,
you entangle usual kind of global symmetries with fermion number, for example.
I see.
Just make sure, are there other people have questions? Maybe other you can ask a bit later.
Yeah, that's
question. Any questions more? If not, Muchas gracias. Thank you very much, Jaume, for the wonderful lecture. Thank you. Let's stop recording. Thank you.